Welcome to this introduction to ROMAS, our rocket, orbit, and missile analysis system. For further information, you can reach us at our website, rocketscienceprograms.com. My objective in building ROMAS was to provide a high-fidelity, fast-running set of aerospace programs exclusively for the Mac. Got tired of finding programs I was interested only available on the PC. These would be for engineering students, future rocket scientists, and even good enough for aerospace engineers. I wanted to make ROMAS menu-driven and easy to use. User can select US units or metric units. I got tired of finding programs only in metric units. I also wanted to optimize the use of MS Excel. It has great math capabilities, and I wanted to use those to prepare some of the input files where some calculations were required. It also has great graphing output capability for the visual effects. When I maximize the use of online map plotting programs, not need to build that in. I wanted to provide excellent printed and visual output, and I wanted to make the program sort of self-documenting so they would be very easy to recover, reuse, make a simple change, and make another run, review the results, and make another run. In summary, I avoided the use of cartoon graphics. I just wanted to make a solid technical and engineering data available with great visuals. Each program comes with its own user guide, and ROMAS was a major effort. It took more than 3 years and over 13,000 lines of code. ROMAS was built around 6 major programs. Rocket 2 estimates launch vehicle performance. The utility program builds input files that help Rocket 2 and also can create basic design data for launch vehicles and orbital transfer vehicles. Third was Earth Bench. It provides map plotting capability for mapping the subpoints of radar or command and control communication sites or geostationary satellites, and also provides, which is important, the constant Earth data that is necessary for all ROMAS programs. Earth Bench determines the orbits, what their coverage is, and how they may be covered by ground-based radars. ASAT program simulates an attacker for anti-satellite engagements. It identifies both target and attackers. Finally, the Missile Bench program simulates ICBM or SLBM trajectories and detections by radars and geostationary satellites. These 6 programs comprise 4 major capabilities or products. And as you can see, Rocket 2 requires the utility program. All programs require Earth Bench to be as a support program. I will now address each of the 6 programs, starting with Rocket 2. Rocket 2, as I've indicated, is designed as a high-fidelity point mass spherical Earth simulation and orbit determination program that does have optimization capability. The input and output files are saved in a structured environment and grouped by case number, so all input and output files are grouped together. The features considers considerable number of values as listed in this first bullet under Rocket 2 features. 50 to 60 different numbers are required to run the cases. The major flexibility comes from the mission planning and control, which allows complete control of ignitions, shutdowns, when to drop stages, what their weights are, any other mass dropping events or boil-offs, and the throttling of thrust up and down as done as some vehicles approach max Q. All of the above features and considerations are under the complete control of user inputs. The modeling is accurate to 1 pound of mass from liftoff to injection. You can automatically iterate payload and payload mass to find optimum configurations, and all of this can be used to investigate new designs, model existing designs that you're interested in, or possible improvements to existing designs. The utility program provides reformatting of information you may have on launch vehicle components or solid rocket motors that may not be in the format that is needed by Rocket 2. It will reformat it into the correct formatting. It is to reduce the complexity and runtime of running the Rocket 2 program, so this is why it is done offline in the utility program. The utility program also looks at optimum Holman transfer burns, deciding on orbit transfer stages design, and helps with new designs. Key features: it prepares or updates data files for the Rocket 2 program. It computes key performance data for solid rocket motors that you may get from rocket motor manufacturers. It can also compute burnout velocities that are required for particular parking orbits, which may be your objective parking orbit, or it will also tell you what the final orbit is for a given set of burnout conditions. It helps in the preliminary launch vehicle design, the design of orbital transfer stages, and other upper stage designs. The Holman transfer stage burns provide you the optimum 2 burns required to get from the initial parking orbit to the final orbit desired. The Orbit Bench program provides capabilities that I found useful when I was an orbital analyst, and it involves the plotting of orbit's ground tracks, how sensors will see those orbits and satellites, and what the areas of coverage and areas of interest would be for a given orbit. Specifically, features: you can build either circular or elliptical orbit ground tracks. You can build a constellation of circular orbit ground tracks. You can determine the coverage of those orbits by C-cubed ground stations when they have access to exercise command and control of the satellite, and also provide look angles for ground-based radar sites when the orbit, the satellite is in orbit. The satellite orbit is in coverage. It also helps determine satellite sensor coverage given a set of cells in an area of interest, and all plotted for map output programs. Here is an example of my favorite map plotting program. Shows 2 orbits that were generated by Orbit Bench. You can see the start of the orbits indicated by 1 and 2. And this is one of the 6 different types of maps that are available for plotting data. EarthBench provides useful tools for doing Earth navigation, determining the subpoints for radar, C-cubed, and GeoSat map coverage, and the third item is providing constants for use in the ROMAS system. Specific features: solving Earth navigation problems with starting latitude and longitude, using a azimuth and distance to get to point 2, or having point 1 and point 2 and finding the azimuth and distance between them. It calculates the subpoints for plotting out radar C-cubed coverage. It also plots out the coverage for 3 kinds of GeoSat coverage. It also has the ability to build tables of slant range charts for visualizing those kinds of problems. And the last feature is that it provides a set of data for the Earth data that is used by all ROMAS programs. All ROMAS programs access the EarthBench program to get the data. This ensures you are using the exact same data for all 4 ROMAS programs. The ASAT bench programs provides tools to understand anti-satellite engagements between target and attacker satellites. given a basic characteristic of the attacker weapon system, which is essentially range. As far as features go, you can build a target circular or elliptical satellite orbit for one or more revs, or you can build a target circular orbit of constellation of satellites, again, one or more revs. Then build the attacker circular or elliptical satellite orbit for the same period of time. You'll then define the kill range for the attacker satellite, run the attacker orbit against the target satellites, and it will identify those times and locations where the target satellites are within the kill range of the attacker. The output is in tabular form, identifying attack times and locations, and also provides plot points to show target or attacker orbits, or where the target satellites could be attacked, or you may overlay all three outputs for a single plot. The Missile Bench program provides a useful set of tools to understand ballistic missile trajectories and the coverage of those trajectories by ground-based radars, geostationary warning satellites, or even anti-ballistic missile defense systems. Key features of this program first allows the user to make a reference material table of ballistic missile trajectories with varying burnout conditions. It allows you to create simulations using spherical vacuum earth. Options include a rotating earth or a non-rotating earth. The trajectory shaping can be controlled by being minimum energy, burnout velocity, or apogee altitude fit. Calculations and detections by radars, missile warning geosats, or ABM systems. That concludes the summary of the ROMAS programs. If you're interested in more information about these programs, you can visit our website at rocketscienceprograms.com, or if you wish to ask some questions, you can reach me at developer.romas@gmail.com. Thank you for watching.